Math Kids. Today we're going to talk about section 2.4 and start with example 1. You'll see on the screen I have a definition for continuity, and we're going to use that definition to prove that these functions are continuous. Okay, so k can be any constant in this case. So we're going to use the left-hand side of this. So the limit as x approaches c, and then we just plug in our k for f of x, and then we need to show that this is going to be the same as f of c. So if we have a constant right here, the limit of a constant is just that constant. And if we do f of c, we're always going to get k, because it doesn't matter what our x value is, we always get k. Alright? Now, let's get rid of this. There's a part b. G of x this time is equal to n, and then n is contained on the set of all whole numbers. Okay, for this, we're going to look at the limit as x approaches c of x to the n. And we know the limit of that, we can just plug in c, so it's going to be c to the n. Now, we need to show that f of c is equal to this, so if we just plug in c right here, we get c to the n. Since those are the same, we know that it's continuous. Now we're going to try example 2. So it says to discuss the continuity of this piecewise function. So we have f of x is equal to x, 3x. Oops. And this is when x is less than 1, and we're in between, and like that. Okay. So let's graph this just to wrap our head around it. So this is just y equals x, and that happens all the way up till we get to 1. It's going to go forever that direction. So that's that. Then we have a constant function at 3, closed on both sides. So that's that piece. And then x, so we go up 1, over 1, up 1, over, okay. So it's going to share that point and then continue going. Okay, so that's what it looks like. Visually, we can see that we are not continuous right here, so we should expect x equals 1 is discontinuous, or the function is discontinuous at x equals 1. But right here at x equals 3, it actually is continuous. Now, what really all we need to show is that at x equal 1, the one-sided limits exist, and so if we're looking at x equals 1, as x approaches 1 from the negative side, we're going to get positive 1. As x approaches 1 from the positive side, we're going to get 3. And so there's no limit there, so it can't be continuous. Okay. And then at x equals 3, as x approaches 3 from the negative side, x approaches 3 from the positive side, we see that both of those are going to give us a value of 3. And if we, moreover, that on its own does not prove continuity, but we also need to look at this and this and make sure that if we plug in this value, we get the same value. So if I plug in a 3 here, I get 3. So f of 3 gives me 3. And then here, f of 3 still gives me 3. And so both criteria are met. The limit has to exist, and they have to be, like the point has to exist in the same place for those. You might be wondering, like, when would that ever not happen? For example, we could have a situation where there's an open dot here, it's removed, and then we have something like this. So the limit, if this was the same graph over here, the limit from both sides is still going to be 3, so this is still going to be met. But if we try to plug in that value of 3 down there, it doesn't exist in the same place, because 3 is going to exist at, maybe 4 right there. Okay, now we're going to move on to example 3. Okay, so we have the limit as y approaches pi thirds of sine y. Then we also have the limit as x approaches -1 of 3 to the x square root x plus 5, like that. Okay, so if we try, the first thing we want to do, we always want to just plug this in and see if it works. So sine of pi thirds, we plug that in, we get a value. If you want to do it by hand, you can. So 1, 2, 3. This is our pi thirds, and that's 1/2 comma square root of 3 halves. Sine is the y value, so that's square root of 3 halves. Hopefully you feel comfortable with that. If not, let me know. We can talk more about it in class. Now over here, we're going to just try to plug it in once again, see if any issues come up. 3 to the -1, -1 plus 5 under square root. So it's just going to be square root of 4 on the bottom, which is really just a 2. And then this 3 can come down to the bottom. So we have 1 over 2 times 3 and 1 over 6. So didn't have to do anything special on that one, just worked out. Okay. Okay, so we want to evaluate the limit as x approaches 2 of x using substitution. So this function, you may or may not know what it looks like, but it looks like this. And it's just kind of stepping up by 1, and the widths are just 1 as well. So we can't use substitution on this one because it is not continuous. Specifically at x equals 2. So if we look at x equals 2, this is like x equals 1, this is x equals 2. We see that the left side limit is at 1, but the right side limit is at 2. Okay. And that's essentially it on that one. everything for the video. If you need additional help, please come to MathLab. Until then, calculator.